Good day everyone, my name is Bianca Desiree Galang and I am here to discuss the MOSFET amplifier circuit. First of all, what is the MOSFET amplifier circuit? It is a short for metal oxide semiconductor field effect transistor, and it is an excellent choice for small signal linear amplifiers as their input impedance is extremely high, making them easy to bias. For a MOSFET to produce linear amplification, it has to operate in its saturation region, unlike the bipolar junction transistor. But, just like the BJT, it too needs to be biased around a centrally fixed Q point. Furthermore, MOSFETs conduct through a conductive region or path called the channel. We can make this conductive channel wider or smaller by applying a suitable gate potential and electric field induced around the gate terminal. Furthermore, we are going to discuss the advantages of the MOSFET circuit. It provides a greater efficiency while operating at lower voltages. The absence of gate current results in high input impedance, producing a high switching speed. They operate at lower current and draws no current. They have a higher input impedance compared to the JFET. They have a high drain resistance due to lower resistance of channel. Next and last is they are easy to manufacture. But there are also disadvantages for the MOSFET amplifier circuit. The layer between the gate and channel is very fragile, which is vulnerable to electrostatic damage during installation. With that, it requires well-designed circuit to avoid the issue. Furthermore, it has a short life. It requires repeated calibration for accurate dose measurement. And lastly, they have a very susceptible to overload voltage. Hence, due to installation special handling, it is to be required. There are types of enhancement MOSFETs, and these are the NMOS and PMOS. For my MOSFET circuit amplification, I am going to discuss and use the NMOS. For the NMOS, the substance semiconductor material is P-type, while the source and drain electrodes are N-type. The supply voltage will be positive. Biasing the gate terminal positive attracts electrons within the P-type semiconductor substrate under the gate region towards it. Even if I am not going to use the PMOS, I will still discuss it. First, a negative gate potential causes a build of holes under the gate region. The N-type substrate creates a P-type conductive channel. The more positive potential we put on the gate, the greater the buildup of electrons around the gate region and the wider the conductive channel becomes. This flows enhances the electron flow through the channel, allowing more channel to flow from the drain. There are also types of MOSFETs. First, we have the enhancement type. For the enhancement type, the enhancement mode of MOSFET is commonly used type of transistor. This type of MOSFET is equivalent to normally open switch because it does not conduct when the gate voltage is 0. If the positive voltage is applied to the N-channel gate terminal, then the channel conducts and the drain current flows through the channel. If the bias voltage increases to more positive, then the channel width and drain current through the channel increases to some more. But if the bias voltage is 0 or negative, then the transistor may switch off and the channel is in non-conductive state. So, now we can say that the gate voltage enhancement mode of MOSFET enhances the channel. Next, we have the depletion type. The depletion mode of MOSFETs are generally known as switched on devices because these transistors are generally closed when there is no bias voltage at the gate terminal. If the gate voltage increases in positive, then the channel width increases in depletion mode. As a result, the drain current through the channel increases. If the applied gate voltage more negative, then the channel width is very less and the MOSFETs may enter into the cut-off region. Depletion mode MOSFETs is a rarely type use of transistor in the electronic circuits. The applications of the MOSFETs amplifier circuit. First, MOSFET amplifiers are extensively used in radio frequency applications. Next, it acts as a passive element like resistor, capacitor, and inductor. The DC motors can be regulated by the power of MOSFETs. And lastly, high switching speed of MOSFETs make it an ideal choice in designing chopper circuits. Now that I already discussed a lot about MOSFET amplifier circuits, we are going to discuss this using the LTSPI simulation.
Good day everyone, my name is Bianca Desir Galang and I am here to discuss my LTSPI simulation. First, we are going to make the circuit. We will first add the voltage. We will have the voltage 1 here and the voltage 2 here. We will also add the resistors. You will have resistor 1 here, resistor 2 here, the RD in here, the RS, and the RL. We will rename this as RD and this as RS and this as RL. Now we will add the capacitors. We will rotate it, Control R, and we will add the capacitor 1 here and then the capacitor 2 here. Last, we will also have the NMOS for our MOSFET circuit. And for our NMOS, we will choose BSP89. Now we are going to add the wires. So first we connect the voltage to the capacitor and then the resistor 2. Next, we are going to move the resistor 1 for us to connect it to the resistor 2. Now we will add the wire. We will cut this part and then add the wire again and connect the R1 to the RD and connect it to the MOSFET and then the RS and connect it back. And we will have the connection here from the capacitor 2 to the RL and then close it here. Then we will also have a wire from the V2. We will cut it. We will have a wire. Now we are going to put the labels or some names, and we are going to add some label net. First, we are going to add the VG. And we will place it in here. We will also add the VD and place it in here. We will have the VS, place it here. We will also have the V out or the voltage output. And we will also have the voltage input. Now we will put the values for our components. First we have 10. And then in our voltage one, we will use a sign or the sin. We will have 0, 100 M amplitude, and 1 kilohertz for the frequency. Next, for the value of R1, we will use 120 kilo ohms. For the R2, we will use 50 kilo ohms. For the RD, we will use 350 ohms. We need to move the RS. So for the RS, we will be using a value of 75 ohms. For all the capacitors, we will use 10. And for our RL, we will be using 15 kilo ohms. Now that our circuit is complete, we can now use the .op command so we can look for the operating outputs. But first, we need to add a ground. So we will add it here and then connect it with the wire. Now we are going to use the SPICE directive and type OP for us to see the operating points, and you can place this SPICE directive anywhere, but I'll just place it near the ground. So if we run it, we can see the value of our operating points, and we will be using all of this later. Now, since we are going to get the bandwidth, the power, and the voltage gain, we are going to use the transient command and then the MES command. I will just type all of it in here. I will type the transient as tran 0, 10M0. I will use for the voltage output peak to peak and the voltage input peak to peak as VOPP, PP, V out, and then that MES VIPP, PP, V out, a V in, since it's a voltage in. And for the average voltage gain, we will use that voltage AV, param, and since its value is equal to the voltage output over voltage input, we will input VOPP over VIPP. Next, we are going to measure the power, so we are going to use that MES IOPP PPIRL, and we will also going to use that MES IOPP PPIC1. And for the bandwidth, we are going to use these measurement commands or the .mes commands. .mes T1, find time when v in is equal to 0.5 m, and then we will just copy paste it so it would be easier. That Control C and then Control V and just change it to 2 and add cross 3. These are going to be used for the bandwidth, and furthermore we are going to add that mes, since for the we're going for the input, and then param, then we will add T1, T2 minus T1. And then again, we will use this. We will copy and paste. But this time, we will use TA. And instead of input voltage, we are going to use voltage output. And then we are going to copy paste it again. But this time, we are going to use TB and voltage output. And we will add cross 3. And finally, we will have the mes f out param 1 TB minus TA. Now, since we have the transient command and the mes commands, we can now run the simulation. First of all, we can measure the value of the VG, which is 2.94 volts. And then we're going to delete it so we can measure other things. Now, we can also measure the value of the VD, which is almost 4.56 volts. And if you're going to, we have the 4.27 volts. We are going to look on this side. Now we are also going to measure the value of our VS, which is 1.16 volts. And next is we are going to measure the value of our RD, which is 15.4 volts, and we're going to delete it. And lastly, we are going to measure the value of our RS, or the current, which is also 15.6 volts. And then for that, since we have the mes commands, we can measure the exact values by just clicking the view tab and then selecting the SPICE error log. And as you can see, here's the value for the peak-to-peak voltage, the average voltage gain, the power, and the bandwidth. And that's all for my simulation circuit explanation. I hope you learn well. Thank you.
Now that we already learned a lot from the LT SPICE simulation, I am now going to discuss the sample computation for the computed values. Since we have the given of 10 volts for VDD, 120 kilo ohms for R1, 50 kilo ohms for R2, 350 ohms for RD, and 75 ohms for RS. So, when we compute the value of VG, we will use the formula VDD multiplied by R2 over R1 plus R2. Substituting the values, we will have 10 multiplied by 50 over 120 plus 50, and the resulting value is 2.9412 volts. For the VD, the formula is VDD over 2.2, and substituting the value of VDD, we will get 4.54 volts. For the ID, we will be using VDD minus VD over RD, and with that, substituting, we will get 10 volts minus 4.54 volts over 350 ohms, and the resulting value is 15.60 milliamperes. Next, we will continue solving. For the value of VG, our formula is VGS plus IDRS. So VGS is equal to VG minus RDRS. Substituting, 2.9412 minus 15.60 times 10 raised to negative 3 multiplied to 75, the resulting value is 1.77 volts. For the VG, we will get VGS plus VS, and for the VS, our value will be VG minus VGS. Substituting, we will have 2.9412 minus 1.77 volts, and the answer is 1.17 volts. For the IS, we will use VG minus VGS over RS. Substituting, we will get 2.9412 minus 1.77 over 75, and the resulting value is 15.62. Now that we have the values for the computed ones, we can now compare and contrast the value that we got from the LTSpice and then the values that we computed. For the simulated values, the VG is 2.94, VD is 4.57, VS is 1.16, and the ID and IS have the same value of 15.56 milliamperes. However, for the computed value, VG is equal to 2.94, VD is equal to 2.54, VS is equal to 1.17 volts, ID is equal to 15.60 milliamperes, and IS is equal to 15.62 milliamperes. As we can see, there is a slight discrepancy between the simulated and computed values. This is expected because on the simulated one, the values are exact, while in the computed ones, while processing or while computing, we tend to round off some answers, so as a result, there would be a small or little or no discrepancy on the resulting values. For the references of my project, I used the electronic tutorials and search for MOSFET amplifier, and then I also used the Electrical Fund blog, and lastly, I also used Electronics Hub. These are all the things that I used in my project, and I hope you learned a lot. That's all. Thank you for listening. Again, I am Bianca Desiree Galang from B16, and this is my project for Electronics Devices Laboratory. Thank you.